Viale and by Gustavo on the respective parts where they have been contributing to that recent paper that was submitted approximately a week ago. This paper is about measuring the horizontal Reynolds stress. And the horizontal Reynolds stress plays some particular role in solar physics because it does explain, as we now understand, the differential rotation on the sun. However, it was originally actually a quantity that was determined from observations. So what was determined from observations is the so-called proper motions of sunspots.
Horizontal means solar context? What does horizontal mean?
Horizontal means
parallel to the surface.
Horizontal means parallel to the surface, right?
Okay, so in solar context.
In solar context, yes. So you're thinking of the sun like this, and then this is vertical, and this is horizontal. And of course, if you're looking at the sun, you can only see horizontal motions, and those one can actually see. So you see sunspots on the surface of the sun, often they come in pairs, and if you actually observe them for in a day's interval, then the next day their position has slightly changed. They have been moved, for example, upward a little bit, and maybe even a little bit to the left. And then what is done is you calculate the deviation from the average flow. So you calculate the fluctuation that we sometimes call either with the lowercase character or with the uppercase character, which is the actual velocity here in this case of the sunspot. But you subtract from this the mean flow, and the mean flow is consisting both of meridional flow, which goes towards the poles on the two sides of the hemisphere, two sides of the equator, and of course you have the differential rotation, which is fast and long.
How do you measure the mean flow?
How do you measure the mean flow?
Yes.
Again, also the sunspots, and you average. So in all cases you measure, that's also what you do in a turbulence simulation. Suppose you have a turbulence simulation, you can ask how do you measure the flow, and you just look at the simulation with the variable mu.
So that's
then the question is how do you do the average? In that case you average.
So that's not the speed of the quiet photosphere, right? In principle, it doesn't have.
It is indeed not the same, which is a good question because they move, and so do magnetic tracers. They all move with a speed that is different from the photospheric velocity of the plasma. That was for a long time not well understood. You remember, as we had yesterday in the group meeting, we had this plot here, of course. So this is what you see at the surface if you do a Doppler measurement of the photospheric plasma at the surface. If you, on the other hand, measure a sunspot, it comes in with a different velocity. You don't know really what it means. And so do magnetic tracers. They all come with velocity that is somehow at some point along this line, although there is not necessarily a clear connection between the two. So what I'm having here is phi omega versus radius. That's now
the velocities are all kind of large scale. So you don't go back to the...
No, I mean this is what we normally would call small scale.
But it doesn't go to the granulation step.
I see what you mean.
Can you trace the velocity of each granule?
Yes, that's a good point. So the typical velocities that we see are they are still only comparable to the velocity. So indeed, so the velocity that one gets here is one which would vary on a time scale of days or something. Whereas the time scale velocity that if you actually were to observe really on with a much better resolution on the surface, you should get much shorter time scales as well. And how this is modifying the result is, of course, not yet completely clear. I mean, this really has to do with the fact that the fluctuations themselves could be either governing only the slower parts, or they could be covered, which are still slower, which are still faster than the slowest motion here. This is steady, of course. I think there would be a continuous spectrum between these. And then what is done is you measure what Petri will call now Q theta phi, and that is a correlation between two components of the velocity field. So it's this thing, which is a vector, but you take the theta component and you take the phi component, and you multiply them, and it's a one-point correlation. So you do this at one particular point, and you average this. And the average then goes over all longitudes and latitudes, and it goes also over time. It goes between cycle 11 to cycle 22. For example, for the latest, which I will show you in a moment. Oh, anyway, so and this relation is called the Ward relation, and Fred Ward was the first one who actually determined that from observations. And that's a paper of 65. And at the moment I'm puzzled because it's negative, but I think it was actually explained in the book that you can read that many times.
It's only 200 pages.
No, it's the caption to the figure, which of course I admitted.
Sorry.
Yes.
Like, is the study particularly of general stress and the motion of a sunspot or in general?
It's the sunspot.
Okay, so you measure the Reynolds stress on this motion, but then you assume that the motion of the global velocity is that of the sunspot. So kind of a self-fulfilling stuff or not?
I mean, you get some kind of a velocity. If you really think that the sunspot reflects the motion of the plasma, you can measure its velocity, and you can also average it. So you get two things out of it. You
Yeah,
get
okay,
the
but
average and the actual velocity.
the Reynolds stress, you use that velocity. The same.
Of course. You subtract the average, so you get a fluctuation, and then you take the two components and multiply them. That's the same one. Here is now the more recent result from the paper really between cycles 10 and 22 by the paper from Pulkkinen and Tuominen. And they have it really here as a function of latitude. So you remember the Ward picture was negative, so he was most likely in the southern hemisphere. And Petri still doesn't know. But here we see it for sure, because in this paper they plotted this quantity Q theta phi as a function of latitude. And in positive latitudes it's positive, and in negative latitudes negative. Is that surprising? And the answer is yes, first
So
of all.
what's the difference between the dotted and the solid line?
I don't know. The dashed lines show the numbers of measured
Okay.
CS.
Oh, so that's why they get the large errors.
Yes,
Yeah.
yes, that's a good point. Yeah, so there's large errors because there's zero observations hardly.
You are theta?
What?
Or theta phi?
Q theta phi, the same quantity. And so we see now it's positive. So what is known about the Reynolds stress? People know about viscosity, right? I mean, that's what you do if somebody does a simulation, they have the Reynolds stress, either you solve it for yourself, so you have your equation, which says, of course, u by dt is equal to minus, and then you have e by dx j ui uj. Or, as many people do, you'd actually do this for the average. So in this case, you have an average quantity. And then, of course, you have to have two things here. You have, first of all, average flows that we all know how to calculate. But there are the products of the fluctuations, which are here these fluctuations. And people make an ansatz for this. They simply say, okay, maybe it's a small scale, that's probably just diffusive. Let's describe it as some turbulent diffusion. Okay, and then they say ui uj is equal to a negative viscosity turbulent, minus, because on the right-hand side, it would enter like something like a plus del squared of u average. That's what you want it to be. And of course, in terms of the stress, which is underneath another divergence, what you would write is, here in this case, the I, let me write it as commas here, ui comma j plus he takes the symmetric part of the tensor. This tensor is symmetric, so you better be sure that everything you make up from this is also symmetric. And so, of course, if this is not symmetric, in many simulations, by the way, that's what I was sometimes saying, people say they put some turbulent diffusion, they just put this, and then they don't put this, and then it's not symmetric, and then, of course, they can produce vorticity. And then they say this vorticity is not even artificial, it's actually a subgrid scale. Okay, so now back to the story. So if that's all it is, we can work out what is now this quantity, u theta, u phi, fluctuations, and of course that would be equal to, and of course people know how to do it in Cartesian coordinates. We should just write, which is not the case here, of course. So Drew would know how to do it correctly. Hopefully. And of course, the only thing you do is you just put a semicolon here. That's correct, of course. And what that means is the following: it's minus nu t times the omega, which is the mean flow. So we basically say u phi is equal to omega times omega, if you like that. But if some people don't like this, so then it's r sine theta. That's your u phi, the mean flow. Then the quantity is like this. And then now I forgot again. What was the sign, I think? Was it the sign?
Yes.
Yeah. Okay. So everything okay, or is there a problem? What? Okay? Everything's okay?
No.
So what do we, I mean, obviously, what is this in the sun? Angular velocity, we go from the pole to the equator. What happens in that case? How does the angular velocity look like as a function of?
Increases.
Hmm?
Yeah. Increases.
Yes, exactly. So often people draw it like this. So it's the equator is faster, and therefore this quantity is positive. The sine theta is always positive. Nu t is hopefully also positive, otherwise your simulation would blow up.
Mm-hmm.
And so this whole thing is therefore negative. Minus. And then, of course, on the other hand, it's observed to be positive. So either now you say this really has nothing to do with anything. So you measure this, but you basically say you don't really actually measure this, it's something else. Because it doesn't have anything to do with, sunspots have nothing to do with velocity, which you could say. Or you say there is really a problem, and something is missing. And that's what indeed a number of people have been saying. And I think this really also goes back to people like Peter Gilman. So here, this plot you actually don't find in the paper by Ward. I was desperately looking for that. He only has tables. So everything is the result of table. And then, of course, if I wanted to show a table, that takes longer to understand. So what he has is, this is from the book by Rüdiger, which especially has now, where the Ward line is, I think, in this one. What do you see now? And then the other picture is by Gilman, G, and Howard, I think. Gilman and Howard. And then this, maybe this line. So they have this negative correlation, and that is probably on the negative southern hemisphere, otherwise everything was
Yeah, the thing here is that Rüdiger and Hollenbach state that the horizontal cross correlation is never negative. And then when they describe this figure, they say change the sign of the horizontal axis for comparison with equation 3.1.
Yes.
Which is the horizontal stress.
Yes. So they have defined it with a negative sign somehow for some reason. So it's confusing, of course. But as often in astrophysics. In astrophysics, you would never normally plot something like this. I mean, you would not plot this versus this. You what in astrophysics normally do is you plot this versus this. Right? And one example is of course.
Actually, yes, look at the equation. So there is no.
Oh, that's what so they have really defined it. Yeah.
Yeah.
So what they have in that book is actually not this one, it's directly this one. So they basically plotted this quantity, and then of course they say that is indeed negative. Okay, so I don't know. And then, of course, this is the answer for this is that is of course not the differential rotation. That's of course not just the differential rotation which produces the stress, but there's another term which is called the so-called lambda effect. And the lambda effect is like the dynamo alpha effect, which is then proportional to the angular velocity directly itself. That's what is called the lambda effect. And now there's two different parts of the lambda effect: the vertical lambda effect and the horizontal lambda effect. And of course, we're talking about the horizontal one, because it's horizontal correlation, and that has been calculated in a number of simulations. The first one is here by Pulkkinen and four other authors, of which I was one. And so you see in the south, this degree south, it comes out to be negative. In agreement with the full observed sunspots thing. It was actually a wonderful agreement, and you notice that it has a minimum at 30 degrees. Perfect. Next one is here the simulation by Riator.
Do you see the same behavior with the previous data?
Actually, you do see something very close to that, and that is parameterized by two different functions, which are called W1 and W2. And there are in this particular, there are these. There's a table.
For those observations, you get nothing above something like 40 degrees latitude. So you don't see
Yes, that's right. The sunspots can't be seen here beyond this. Because this is the simulation for the first time in a full sphere by Riator and company, but this in that case, also including myself, in that case the thickness of the zone was not between, as we normally would do, between 0.7 and 1, but it was between 0.4 and 1. And you think, why the hell would you do such a thing? And by the way, it was also incompressible. And that was also crazy. I mean, first, incompressible, you could say that's okay because that's a simplification.
Incompressible or elastic?
It was incompressible. And the reason was it was actually not for the sun, it was for the Earth. And of course, the Earth has a thickness of approximately exactly from here to here. So it was a simulation for the Earth, and so in principle, the Earth should also rotate differentially. But that nobody has seen yet because this would be the iron core, the outer iron core. So that is, but one thing you notice.
You mean the Earth's core, not the Earth.
No, I'm talking about the Earth core. So you have heard it from Gazina, what that all is all about. So the Earth has a core.
Yes.
So far, so good. But then it actually has an inner and an outer one. So what's the difference between the inner and the outer one? So this is a core. What? The inner core is smaller. Yes. What else?
Solid.
Yeah, but why the hell is it solid? I mean, the pressure is higher, right? So normally you would think if you put things under high pressure, it melts and stuff. Yes, in this case it does in fact go solid. It doesn't melt. Okay.
Main point is your one is the outer radius of the core.
Actually, what I should have said is in the inner parts, of course, it's much hotter. And then, of course, you would agree that when you make it hotter, it doesn't just become solid, but it becomes liquid. And here it doesn't because the pressure goes even higher. Okay, but the other thing you see is the minimum has now already shifted further away from 30 degrees. So 30 degrees would be at 120 co-latitude. And now the reason for this whole paper that Kapyla will now tell us about in a moment is that there were these papers, this paper by Hupfer, which actually had a minimum even closer to the equator. Look at this. It has an extremum at something like 7.5 degrees.
What is co-latitude?
From the pole, from the equator to the pole.
Ah, so you just add 90 degrees.
This is the actual angle you use. Spherical coordinates.
Okay.
And just have it here. Don't forget to sign up for this, of course. That's
So Patrick,
Yeah, so call,
Okay, what is the
while Patrick is setting up,
what is the sort of the differences between simulations? Like these words.
maybe higher resolution, but that, as Patrick will find out, there's another reason which nobody realized, and that is the Rossby-Coriolis number, sometimes also called Rossby number. So co-latitude is sort of always one something minus the latitude. So if you talk about a co-dimension, what is the the dimension of a sheet of paper is 2, right? So what's that? It's co-dimension. What's it? What?
1 plus 1.
No, it's something is minus.
What's the question?
Co-dimension of the
So you take is the embedding dimension minus the dimension is the co-dimension.
Plus 1. Plus 1. Yeah, take 1 plus 1.
1 plus 1, but that gives 2, right?
if you embed in time domains. Then 24 minus, yes, that's 1 plus 1.
Okay, so this peak in the horizontal stress is not the only reason, but one of the main reasons why we decided to do this in spherical coordinates. And this is actually a talk that I gave in Potsdam, so I may probably skip some slides, especially when almost half the people here are also authors in this paper, so they probably know most of this. So what is the use of the Reynolds stresses, turbulent heat transport? The main use, as Axel was telling earlier, is that they contribute to the angular momentum balance and then to define the rotation profile of the Sun. So what we know from the surface observations is that the equator is rotating faster than the poles, and then from helioseismology we know the structure of the differential rotation within the convection zone. And what is important to see here or bear in mind is the surface shear layer, which is often talked about here probably, and also the Takob line. And this is actually where the radial shear is concentrated in the Sun. So within the convection zone, there is very little radial shear. And you see that the isocontours of rotation are not aligned with the rotation axis, which would be vertical here. And this is important to remember when we are comparing with simulation results. And another thing which is not shown here is the meridional circulation, which we know, again, near the surface, it's always towards the pole, and but helioseismology doesn't really tell us where it's coming back. So many dynamo models, especially the flux transport models, rely on a particular type of meridional circulation. So you need, in those models, you need to have a return flow which is really at the base of the convection zone. But we don't know if this exists. And now, what is shown here, this is one of our simulations, the rotation profile from our simulations, and we see that now the isocontours of omega are really aligned with the rotation vector. And we only have differential rotation near the equator. And what is generally the problem in sort of direct simulations, not only that the rotation profile is not what we see in the Sun, but also the large-scale magnetic fields behave differently when we have a dynamo. So this is from an earlier paper where we did dynamo simulations, where we see that we get an oscillating magnetic field, large-scale magnetic field, but the propagation direction is away from the equator, not towards the equator in the Sun. So
Why it's not symmetric enough in South Hemisphere?
that is something that we don't really quite know yet. So it might be that we are in a regime where this sort of asymmetry between hemispheres is cited. There's previous work by Fritz Busse who saw similar things, hemispherical dynamos.
It's supposed to be symmetric only When average over long term.
That is also not clear.
No, it's not.
Look at the
I mean,
Here, it's not even if you take a time average over full duration.
Maybe you just have to run it longer.
But you're assuming that you're right about this. That may not be the case. I mean, we know the sun is symmetric, but the sun is one particular parameter. Let me remind you, if you do the same thing for dynamos, there are certain regimes where, for small velocities, the dynamos are dipolar. For larger velocities, the dipolar mode becomes unstable, and the quadrupolar mode is the only stable one. And you have regimes in between for intermediate values of the Reynolds number. If you check dipole, unstable. Quadrupole, also unstable. And you run, of course, you get some kind of a mixed mode. And the mixed mode is on a torus, topologically, and it's stable. So you have a mixed mode which is stable. So if you're now saying it should, if you do a long time average, it's still not symmetric.
But now you can do a simple average.
No, I mean, as I said, it will not reach the extrema. You plot the parity as a function of time. Time and parity goes between plus and minus 1. And quadrupole is up here, dipole is down here. The mixed mode has something in between here. It's more complicated. It's asymmetric in time as well. And so forth. And if you time average, you get something in the middle here. You don't get many of these extrema.
So I mean, your equations are still symmetric.
Yes.
So it is true that in one simulation, right, is forbidden in one direction, but if you do an ensemble average, you put different randomly.
So you mean what is the initial condition?
Then you should get both kind of.
No, because we're talking about solutions. This is an unstable solution. This is an unstable solution. This is a stable solution. So whenever you run any simulation, even if you take different initial conditions, you will only be able to get stable solutions.
Yeah, but then why is on one direction, not for one side, but not the other side? So it should be insensitive to the initial condition.
Well, there's one stable solution, which is this mixed parity. And whatever you get from the simulations is actually independent of the initial conditions. You get one is the same. In fact, there are sometimes cases where there could be two mixed parity solutions. In this particular case, there was one mixed parity solution.
But is it that mixed parity?
So of course, Kapyla doesn't know. Parity, you mean, yeah?
The one that's shown there, is that a mixed parity?
At the moment, it is.
Yes.
And
So you can write it down as a periodic monopolar plus a periodic quadrupole.
you can expand it in higher multiples, yes, and then you will have even odd multiples.
What do you expect about
The byte itself is also.
That's what he has. That's what mix means. Mix means you have even and odd together.
But if you change your initial condition, your random initial condition, do you also have get some different modes?
We haven't
Are
tried.
like flipped, the same but
No,
flipped?
this is again just one point in the
Yes.
parameter space.
Yes.
One particular initial
And what I was drawing on the left is actually mean field. So that means if you run this for 20,000 years, and then average over 20,000 years, then you should get something which is perhaps a mixed mode.
So in fact, at the end of that time, it seems that the northern hemisphere is.
Yeah, at the end, the northern hemisphere is stronger.
Yeah.
So
So I'm not necessarily saying this has to be a pure mode, but if you're saying it must be a pure mode simply because the sun is pure, then that's not the case that we know of convex angles.
So-
The question was not of pure mode, but of symmetry. Anyway,
But how you create the rotation profile, it's just that you take an inner part is have rigid rotation and then you let it involve, or
no, we just have a rotating shell and convection in it.
okay.
And then we let it.
Yeah, but the
evolve.
boundary condition at the bottom
The
has
boundary conditions are stress-free at all boundaries.
Sometimes the referee is asking, so why do you take stress-free? But the answer is because we don't want to put any angular momentum either in or out. So we are not, for example, accelerating or decelerating the fluid in the sphere. In the sun, of course, it's decelerating gradually because it has a wind. But that's very small effect.
Trigger point maybe. You say that again this velocity profile is valid as measuring like sunspots, but actually this is the opposite velocity to the meridional circulation.
Yeah, but that's subtracted. I mean, that's just subtracted. I mean, the meridional circulation is indeed the meridional circulation. But if you plot this versus time, how does it look like? So here you plot your theta, right? And you measure, and it looks like this. Right? So what you do is this, you average. And that's what Kapyla is now using in her simulations. That's the average value, it's a constant. We are using the departure from this. This departure is exactly what this is.
Okay, so let's continue. Okay, so this is very basic, which Axel basically covered already. So we have our equation for the angular momentum, where the Reynolds stress appears. Here it's Rij, which is the same as Qij we had in the blackboard. And this is again the same story with the most simple ansatz that we can have for our Reynolds stress, which turns out to be invalid in the sun. So we would deduce from these figures that we should have a negative turbulence viscosity, which is not reasonable. So we have to have another term, which is the lambda effect, a non-diffusive term, and there is some theory behind this. This is when I was in Potsdam, Günther forced me to use this new figure, which is the latest from their theory. So we have the two components, the vertical lambda effects and then the horizontal one. And the theory of Kichetino and Rüdiger predicts that the vertical lambda effect is always negative and it goes to zero. Actually, if I'm not mistaken, it does go positive here. But for Günther, this was not enough evidence of the positive value.
What do you mean? It's 0.2.
Yeah, it's positive.
Then?
But he says that it's zero.
On the equator?
Yes.
Ah.
It's clearly non-zero. And
No, I think you must be talking about maybe this multiplied by cosine theta or something.
Yeah, that might be.
Which is what enters in the stress.
Right.
So this is not the stress.
No, this is just V here.
Yes.
And V here is just this guy.
Yes.
So then you have to multiply.
By cosine theta in the third equation. Yes.
Right. And what's also seen here is the lambda quenching.
Third line.
Ah, here, yes.
So we're looking at H.
No, V. V. This is V.
No, that doesn't become zero in the equator. I thought it would.
No.
Oh, that's you mean. That should be zero. Okay.
Oh, it's positive here
Yes.
for a few points.
Okay. Mm.
Okay, where was I? Oh yes. So this is the lambda quenching, rotational quenching. So this is the Coriolis number now. So when the Coriolis number is increased, then the stress or the lambda effect decreases all the time. And the horizontal stress here, just this H, this is always positive in the theory, and there's also quenching here, but now the maximum value is obtained for somewhere maybe between 1 and 3, Coriolis number 1 and 3. And what this means is that the radial flux of angular momentum is always inward, and then the latitudinal flux of angular momentum is towards the equator. And these basic results have basically been confirmed by local simulations of convection and also force circulation.
So that's what drives the differential rotation. That's the answer to your question. Why is it non-uniform? And it's because lambda is finite.
Yes. And this was actually also covered by Axel. So this is now the horizontal stress from a bunch of local simulations. So these dotted lines that you can barely see are simulations, and the rest in between is extrapolation. Clever, right? So you get a maximum here. Now this is negative because we are on the southern hemisphere. So there's a huge maximum near the equator. And then this is one of the puzzles that came out of the local simulations. Another puzzle is the vertical stress, which is for slow rotation. We get nicely, at least qualitatively, what the theory predicts. We always get a negative value for the stress. But when we go to rapid rotation, then there is a sign change. So near the equator, it's actually positive. So the radial angular momentum flux is outwards. And this is something that at least Günther is very, very allergic to. So he doesn't, I mean, their theory doesn't predict any vertical or sign change for the vertical stress. So, but this is what we see in the convection simulations.
But maybe Günther is talking about the lambda, not about the stress.
Yes, that's true, okay. So it's for, the lambda is always negative, but the stress can of course change sign depending on turbulent viscosity and large-scale flows. So yes, that's actually one of the points that is often not dealt very deeply in these papers, is that when you get a Reynolds stress, then you actually relate it to just the lambda effects and ignore turbulent viscosity, which is equally bad as doing the other thing, that's assuming that it's only diffusive and then neglecting the lambda effect. So, okay. Okay, there's the other thing, I don't know if we have time to talk about all of this, about the turbulent heat flux. So turbulent heat flux is just a correlation of fluctuating velocity and temperature. And if we have a non-rotating case, then we only have a radial heat flux, so convection transporting heat outwards. But when we have rotation, we can also have horizontal heat fluxes. And here is an example of one of Günther's papers. And this is now the latitudinal heat flux, which is here negative. And negative means this is in the northern hemisphere, and this means that there is a poleward latitudinal heat flux. So there is this leads to a temperature difference between the equator and the pole. And this temperature difference can then drive a thermal wind, which can then break the Taylor-Proudman balance, which is done here by Axel in 1992. And now we want to extend our study to spherical geometry to see if these results also, if they are robust so that they also appear there. Okay, here's the setup. We are not actually going through the whole longitude. It's only 90 degrees, but I have multiplied it here, so it's actually something like this here. But it looks much nicer if we cover the whole sphere. So this is duplicated 4 times here. And this is from a non-rotating run, this snapshot. And we go in radius from 0.65 to 1. And there's a stable layer below, so between 0.65 and 7.7. Then we have convectively unstable layer. And then at the surface we also cool. We have a cooling layer which is convectively stable. And this is fairly simple polytropic stratification. And this is fairly stratified, so we have a density contrast of 100 over the full domain. So from the bottom of the stable layer to the surface, we have a density difference of 100. And yes, I guess there's nothing much more there. So now we come to the horizontal Reynolds stress, and I'll just talk about the spherical results here. So these are now 6 different simulations with 6 different rotation rates. Here we have slow rotation, faster, 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 and this is rapid rotation. And the Coriolis number is equal to 1 in about here, run A4, and then we have something like 3 and something like 6 here. And here it's always less than 1, and we see that there is not really big differences happening on the first 3 runs. And here we see line plots from 3 different depths of the horizontal stress.
Sorry, you said the Coriolism, but what's the Coriolism for the sun?
That depends on the depth. So at the base of the convection zone, it's of the order of 10, but when you come to the photosphere, it's something like 10 to minus 3.
Okay.
So it changes a lot as a function of radius, which cannot be said about the simulations. So here, the Coriolis number is, maybe it changes by a factor of 2 or 3 within the convection zone, but not more than that.
When you're putting the Coriolis number, you're putting it in terms of the base actually.
Of the what?
The average.
Average, yes, okay. I'll write it down. So, Coriolis number is now 2 times omega divided by RNS, which is the fluctuating velocity, the volume average of the fluctuating velocity here. And then KF, and KF is no. Okay.
Yes.
Okay.
So the because we are using this KF, our values are actually smaller pi, factor of 2 pi.
And 0.3, so it's 20.
So your R is 0.35.
The R here is the depth of from the base of the convection zone to the surface, so it's
Yes.
0.3. Okay, so here are two of these simulations, A4 and A5. Or are they? No, I'm not sure. I better check that. Okay, let's see if I can. Yes, it has to be. So this is now the local Coriolis number from 3 different depths. So this is actually showing the differential rotation on this figure from different depths. So we see that in run A4 there is anti-solar differential rotation. So the angular velocity is smaller at the equator than at higher latitudes. Here it's only 30 degrees from the equator. Whereas in run A5 there is assigned there is the opposite trend, so we have a solar-like rotation profile. So the equator is rotating faster than the poles. But we see that the Renault stress actually doesn't show similar flick. So we always have a maximum which is fairly close to the equator, especially at the base of the convection zone, which is the solid line here. And this seems to persist also for the higher rotation rate, although the rotation profile is reversed. And here then these symbols denote data points from local simulations, and now I will let Gustavo explain how these data points were obtained.
Mm-hmm.
So there is
So, very quickly, the simulations that we made were in a Cartesian box, but it was exactly the same stratification and same setup used for the spherical simulation. So the only thing that we changed was the geometry in the pencil code from Cartesian to spherical. And then one of the motivations for doing this kind of simulations was observe if the Reynolds stresses are the same that the ones obtained in previous works, which were done with independent and different codes. Your simulations of 2004 is a different code. It's
yes.
not yet the code. and the Kapyla simulations are done with another different code. And you didn't put the other figure well. For the horizontal,
This one?
no, with the radial variation.
Oh no.
No, okay,
No,
but in the next one, the horizontal stresses that we obtained is, this is from in your 2004.
That's actually one of my test runs, but
Okay, the horizontal stresses are like this.
yes.
The radial profile of the horizontal stresses are like this, and are the same. Well, they compare very well with the previous results. And then you please go back. These dots corresponds to the simulations for, this is A4, right, or A5?
Yes.
A5. E4?
I think so.
Maybe it's it's A4. Okay. There are some difference. For example, the diamonds corresponds to 0.9, so very close to the surface in the box. And for the sphere, it corresponds to this dashed line. So in the Cartesian coordinates, the peak in the horizontal stresses or stress is very close to the equator. In the spherical simulations, the peak is in the bottom of the domain. In the Cartesian is at the top. And then we distinguish that probably the reason for to have this peak very close to the equator is due to the large scale motions that develop in the Cartesian simulations. And this is the so-called banana cells that cover the whole domain. So there is a big contribution of these large scale motions. And one of the things that we did in the paper was try to have the velocity from the velocity field. We subtract the modes. We filter the modes that corresponds to these large scale motions. And then with the filtered velocity, we compute again the Reynolds stresses. And then we obtained a...
Yes, there is actually, on the figure there,
This?
the dashed line is
filter.
subtracting.
Okay, so
Yes.
this dashed line is the filtered horizontal Reynolds stresses. So still, there is a peak close to the surface, but it doesn't have the same amplitude than previously. And if you go to the previous one, the square dots here corresponds to these filtered Reynolds stresses. And here, even though the peak is still at 7 degrees latitude, it fits better with the spherical results. Well, that's basically what was made in Cartesian geometry.
So, yeah, I still have a few slides for Kapyla's contribution.
Can you go one slide? But you don't see the banana cells in the upper picture.
No,
yes,
this
because
is
this is not the same thing. This is a slowly rotating run from different latitude. So this is very close. This is actually at the equator
Okay.
itself. So should we go now for the banana cells or
Later.
later?
Whatever, I mean, how have you placed it? It depends.
I have a few slides in between.
Okay, so we can carry on.
Okay, let's do that. So this is not the only contribution there. This is now the vertical Reynolds stress. And now we see that for slow rotation there is first of all a weak signal, then becomes more prominent negative, which would correspond to a negative lambda effects, vertical lambda effects in accordance with theory. And but when we go closer to Coriolis number equaling 1, then we see that there is this positive patch near the equator, which then grows as the rotation rate increases. And for the most rapid rotation, it's predominantly positive, this stress components. And this is again in accordance with the earlier Cartesian simulations where there was a sign change observed, especially near the equator. And this is now associated with, this is also same as in the Cartesian simulations, that in a non-rotating case or slow rotation, the radial velocity always is larger than the horizontal ones. And this is one of the things where you can expect to find a negative vertical lambda effect. If you have the vertical component of velocity dominating over the horizontal ones. And this situation changes when we go to rapid rotation regime here in line A6. So now the horizontal velocities, these are now the fluctuating velocities, so I have subtracted the large-scale flows. So they almost always are larger than the radial component.
Why does the radial component get a bit not as high as in the other picture? I mean, doesn't the radial flow shouldn't depend so much on the rotation?
Well, it does depend, because when you have rotation, then this tends to suppress convection.
Ah.
So then you can expect to have somewhat smaller radial velocities. And actually the normalization here is
different.
Yeah, you shouldn't compare
Okay.
directly. I mean, this value is much larger than this one here.
Okay.
So it's divided by the RMS velocity squared from these two simulations. So the absolute value might be much bigger here. Okay. Then another thing that we looked at was turbulent heat conductivity, which is kind of the analog of our turbulent viscosity for the heat flux. So for the radial heat flux in the non-rotating case, we can, well, first of all we have the heat flux, and then we can relate it to a term which is proportional to the entropy gradient, and then our turbulent heat conductivity. And we have now computed this from a non-rotating run. We see the result here. And I have overplotted here turbulent viscosity obtained from the same simulation when I impose a large-scale flow on that simulation. And we see that they are of the same order of magnitude, but that the heat conductivity is about 2 times higher than the turbulent viscosity. So we get a turbulent Prandtl number of something like 0.5. Yes. And then we also looked at the latitudinal heat flux, here given in terms of an off-diagonal component of the turbulent heat conductivity, where we have only taken into account the radial derivative of entropy. There would be another term which would be proportional to the latitudinal gradient of entropy, but that's much smaller than the radial one. And we say that for slow rotation, we actually have equatorward latitudinal heat flux, but this changes sign when we go to more rapid rotation. This again occurs close to Coriolis number 1, which is the watershed in many things. Then I have an embarrassing plot here. So this is the latitudinal, or this is the profile of the entropy perturbation. Perturbation now means the deviation from a spherically symmetric contribution. So what we see that we have in this particular simulation at this particular time, we had a entropy gradient, so that we had a large entropy at the pole or near the poles, and then lower entropy at the equator. So we always had a negative latitudinal actually, when this simulation is run longer, much longer, then this is no longer the case, which I only found out after we had submitted the paper.
So what happens then?
Then we get a similar profile as previously. So there's a maximum at some mid-latitude,
Yeah,
and there's a minimum at the high
Yes.
latitudes, and a deeper minimum at
which then agrees with Mish and company, maybe, yeah?
yes, and also our own results. Larger Mach numbers.
So this was for what?
Or this was the low Mach number.
Yeah, this was the low Mach number case. So this is the most rapidly rotating case, but with the lower Mach number. But the problem was that it wasn't run enough at this point,
Aha.
which is a bit silly.
Yes. But and you had the higher Mach number case, and that was done long enough. That is not in the paper.
No. The higher Mach number cases are all of our runs. There is one lower Mach number case, which is this one,
Yes.
which is also in the paper, but
Not long
it's
enough.
not long enough. Yes. So it was still running when I submitted the paper. And I think that was it. And now it's Kapyla's turn. I still have some slides at the end, but maybe we don't have time to go through all of them.
Go to the next one.
You can have this.
So we come back to the banana cells. So this is one of the rapidly rotating runs from Petri's simulations. So here I'll just compare this is in the surface, but this is kind of a meridional cut, and this is how banana cells, if you construct them analytically from spherical harmonics, would look like. And then this is again the same thing from simulations and from spherical harmonics, but in the equatorial plane. So if you count these negative ridges here, you'll see there are something like exactly 16 of them in this whole thing, which means that in terms of spherical harmonics, y, lm, theta, phi, L and M are both 16 for such a run here. And so is the case here. And mathematically, they can, any flow on the surface of a sphere can be broken down into two components: the poloidal flows and the toroidal flows. So, and the toroidal flows are, also contain rotation for. Suppose I put n is equal to 0 here, then that represents the rotation, and other components would represent something like horizontal flows on the sphere. So they are not upwelling or downwelling kind of flows, but they are horizontal flows. And banana cells are characterized by k is equal to L. So in the spherical harmonic y, k, L, we have put k is equal to L. So those are banana cells, and those are strictly poloidal flows. So now if we can decompose all the velocity field in such a simple manner, then the way the horizontal stresses have been calculated from spherical simulations, that is by doing an azimuthal averaging of the velocity perturbations, then we can do a similar thing here, where we can add up over all the spherical harmonics that we can, and then azimuthally average them. Then we have a neat expression like this, where these are the associated Legendre polynomials, and omega is again r sine theta, and Vp and Wp are actually the strengths of the poloidal flows and the toroidal flows. So the idea is that the horizontal stresses, the non-zero horizontal stresses result from the cross correlation between a poloidal velocity field and a toroidal velocity field. But if you do an azimuthal averaging, two poloidal velocity fields will never correlate to give you a non-zero value, because the azimuthal averaging of two poloidal velocity fields will always be 0. So that's an important thing here, because the way the large scale velocity or the large scale stresses or these stresses have been defined. So now if we can do that, so now we can just play around by changing these values k and l, and then we can see what the stresses look like as a function of theta. So again, this was one run which was the slowest rotating run, and then this was the fastest one. So, and these, I mean, if you look at this solid line here, solid curve here, this actually represents the Reynolds stress, the horizontal Reynolds stress due to interaction between banana cells with L is equal to 16 and a corresponding toroidal velocity field which has a different k and l value, but then it interacts with that toroidal field, and it gives, the interesting thing is that it gives rise to these two peaks at around 10-degree latitude, and this is what you see for the fastest rotating runs here. And for the slowest rotating run, we see there are some peaks at the higher latitudes. Now these peaks can result from, not from banana cells, but from Rayleigh-Bernard kind of convection cells interacting with other toroidal flows. So I mean, banana cells can contribute to the Reynolds stresses only when you have higher rotation rate here, and then they are insignificant. So I mean, this is just a simple expression where you can play around with all k and l, and then such a stress can be produced by doing a Fourier summation over all these nodes.
So I think I have a couple of more slides here to show Kapyla's large-scale flows. So now that we have these 6 different runs with different rotation rates, we can look at the large-scale flows, meaning the rotation profile and then the meridional circulation. And what we see that we get only in the largest or fastest rotation case, we get a solar-like rotation profile, where the equator is rotating faster than the high latitudes. And all of the other cases, we get an anti-solar differential rotation. So there is a slow equator and faster poles, and even actually in the slowest rotation cases, we don't really get significant latitudinal differential rotation. It's only radial differential rotation. And the meridional circulation is strong in these few cases. You can see that there is a flow close to the surface towards the pole, and then there's a return flow. And this is very strong, especially in this 1A4, where you see that if we look at the differential rotation parameter, which compares the equatorial and high latitude rotation rates divided by the rotation rate of the equator, we get almost 2 here, which is enormous differential rotation. And another feature here is that we get more and more column-like rotation profiles when the rotation rate is increased. And this is actually, there is some observational results also for this K from basically from photometric observations, or then from temperature maps of stars with star spots. But in most of those cases, K is positive, and K is usually fairly small. So in the sun, we would get something like 0.3 here. Right. So we have there's about 30%.
Like the last point.
Yeah, this is close actually. So this is about 20% here for this one. But for these rapidly rotating stars from which K has been deduced, it's usually much smaller than that, and there is actually a there is actually a trend that K decreases as a function of rotation rates of the star.
But negative or positive?
Positive. I mean, K is positive, but the value is decreasing when rotation rate increases.
Yes.
So
that's beyond the plot.
Right. So I have, I have not included anything from observations in this figure. But this could be something that possibly could be studied with models like this. And of course, having this sort of enormously large negative case, this has not been observed in any star, and it's probably very difficult to measure difference rotation for very slow rotators. Then I just show an animation of anti-solar and solar-like differential rotation. This anti-solar one takes a bit more time to develop, but it's quite dramatic in the end, so it's worth wait. So the solar-like is already established. Now we are beginning to see these. Here the banana cells are more clear because they are bigger, but you can see them also there. And now we begin to see the anti-solar differential rotation. This is for the where we have the largest K value.
It's beautiful.
So in the end, it's pretty dramatic.
Yes. I mean.
They're very, very poor.
Yes.
On the bound. So it's just.
So it's a co-moving frame.
Co-rotating.
Co-rotating, yes.
The angular momentum is the same as the average one.
Yeah. So there, let's look at this figure. So the pole is here. So there, well, I don't know if there's anything fishy happening there. It doesn't seem that there is very drastic effects. Here we can see that there is something strange happening with the pole with very slow rotation rates. But here, I'm not so sure if this effect is so big.
So that other one was run A4.
Yes, it was run A4 and A6.
No, the animation. Oh yeah.
Yes,
A4
so this is A4 and that's A6. And no, I'm not sure if I want to show anything more. Yeah, I think I will quit here.
Okay, good. Thanks very much. Any questions, please? For this latest one on the left, run A4, do you have a picture about a radial cross-section? I mean, the question is, well, the suggestion that we made in the paper with Doppler back in, or the suggestion that was mentioned in the paper with Doppler, which I think goes back to Rüdiger, is that you have antisolar-like rotation if you have dominant radial motions in the equatorial plane. Radially outwards in the equatorial plane. And that could be the case if you have a fairly laminar flow, which is what we thought. But of course, this one doesn't look laminar at all. But one should really look at this in the meridional plane.
Yes.
And you have, of course, some meridional cross-sections.
Yeah, I do have data, but I haven't looked at that. I mean, in that sense, I will of course look at the data. Not this particular part.
And this is completely without magnetic field.
Yes, this is pure hydro.
Okay. So can maybe say that maybe the magnetic field can also. So when you put in magnetic field, also really interact with the flows.
Yes, I mean that's one of the things that's is often mentioned, that when you have a dynamo, then the magnetic field acts back on the differential rotation. But we don't really know what happens if we put a magnetic field into these simulations. Well, the right one, we know that there will be a large-scale dynamo. This is something that I have experimented But on this slower rotation run, I don't know if there is a dynamo, a large-scale dynamo at least.
What if somebody tried to recast the lambda effect and the Reynolds stress in terms of diffusion of angular momentum?
That's something that we plan to do next.
I mean, what are you saying? One should write not in terms of velocity, but in terms of angular momentum.
Yes.
So in other words, you would take omega times the u times rho, maybe even squared, of course, squared. And then you say
That's a sort of quantity, and therefore it can actually be legitimately considered to be diffused. And then you get a pumping term from the coriolis, from the centrifugal force.
so you want to write this like this. Then you would need now the question is, and then you put a ut in front of this, and a minus sign. And the hope would be that this is equal to this, yeah.
Well, I mean, not alone. There's also pumping effects that come in. But
Not at all.
not at all. I mean, there's more. Oh, there. Sorry, you're taking a slightly different direction.
What do you mean this?
What's the big?
Looking at
Yes, so if you're writing it like that, then this right here, there's certainly going to be another term you need, an outwards pumping term.
outwards pumping term.
Yes. If I put a positively rotating velocity fluctuation, that will always try to move outwards. That's the centrifugal force.
One tensor here, right? So how should that?
And then there's going to be like a U. There's going to be a positive UR U phi coming from the fact that a small bit of plasma with an local excess of angular momentum wants to move outwards. So that's not really pumping.
Oh, I see. You're probably. I mean, are you actually saying there should be an epsilon? No, that can't be.
I'm still supposing you're talking about in terms of stresses rather than conservation of angular momentum. It's a little bizarre.
Bizarre? I mean, maybe what you want is the divergence of this.
Eventually, you're going to want some versions of that. Yes. But
that's why you're saying you want the dissolution equation for angular momentum.
yeah.
Then there will be a gamma, you say.
Yeah, it's also going to be there.
Which is a slightly different decomposition in the lambda effect and the turbulent stress that you had before. So I think it's much more natural.
Okay, maybe so. And whether it makes. Okay, we need to think about that. Any other questions here? Comment on that?
And the main reason I'm bringing this up is because I have a hard time imagining you're saying the Lambda effect is transferring angular momentum inwards. And I just find that weird. Angular momentum usually wants to go outwards. So I find the idea of decomposing things into a lambda effect that transfers things inwards is very strange. What? Well, I'm saying if I have a small bit of material and I make it rotate faster than everything that's around it, it wants to move outwards. If it's moving slower than everything around it, it wants to move inwards. This pumps angular momentum outwards. We would do it like that, somewhere. Or something. But whatever happens, if I give them a piece of material a little bit of excess angular momentum, it moves outwards. So all sort of pumping effect moves the angular momentum outwards.
excesses of VR, you expect them just naively to go to V5, you expect naively to go with local excesses of VR.
I guess the challenge is just this quality, because it can be quite the execution.
Well, then that's not, it doesn't actually come as a free term, it comes as a flat pumping. And then there's a diffusion term and momentum. Then you do something worse.
So we are just thinking about the diffusion, but then it can use something that takes place.
Yes. So if you have a term in your equation to just that is acting like a pumping term, it should be moving backwards. Which is a really good reason for pumping terms.
It's fair to make this. And at least you have different angular momentum at different, the same area, different angular momentum at different theta. So suddenly when it's transported better, and you get so far in your negative picture.
So in other words, for the word relation, you would be saying we should look at this.
I haven't thought about longitudinal balances.
But by the analogy, if you talk about momentum, you should be looking at that. And that may indeed be positive then. Actually, how does, sorry, you need to put in, so that means we have sine squared, of course, times this. So who knows about this? How that looks like? Because of course, I need to put in the relative position of that, of course. Oh, no, sorry. And that is, sorry, this is of course increasing, that's also positive. So you certainly don't recover the water relation now. It's even worse than before. You want to change the sign of this, but you don't do it by just multiplying.
I have not given thought to the word relation.
Yeah. Yeah. But it's a counter argument simply.
Well, I just find it very strange that you're not, when you're talking about sort of stresses of turbulent transport, you're talking about turbulent transport and momentum.
What you're talking about is,
when you talk about stresses, you're talking about turbulent transport.
so the picture,
Here we're talking about turbulent transport and momentum.
it has to do with the anisotropy of the turbulence. I'm not sure that is in the argument. The reason why we have this negative has to do with the following. So you plot, let's first do the thing with the vertical direction. For simplicity. So if you have a vertical, if you say, for example, the vertical motions are dominant, and the sun is rotating in this sense, then of course this is being deflected to the left, and this is deflected to the right. And so in this case, you have UR times U phi being negative. So you have a negative lambda effect. And that we know now produces a negative differential rotation.
That's better to look at as diffusion of angular momentum. It's better to look at diffusion of angular momentum.
Yes, but what if you have the opposite sense?
Now you have outwards pumping of angular momentum.
That's still transport.
It is still transport.
So if you draw a source from it,
But the difference is now we've gone from a negative lambda effect to an outwards pump, a centrifugal force motivated outwards pumping term, and a turbulent diffusion of angular momentum, which I think is much more natural language to work in.
So now we go into so now we look at the horizontal lambda effect, and so again we take something which is moving in theta. Well, that's the theta direction here. And now the question is, what is bigger? So suppose, for example,
Actually, what is the angular momentum profile in the function theory? Not the
angular momentum profile.
Yes, not the rotation profile, but the angular momentum profile.
Yeah, this. The angular velocity profile is like this. The angular momentum profile is even steeper because it's just multiplied by sine squared. So here the argument works like this. So suppose the velocities are mostly vertical, mostly theta-wise, then again you have a deflection here. Of course. And you expect in this case a u theta times u phi being negative. that's not what is happening in the sun. So in the sun, you have instead the horizontal ones are being dominant. And then the idea is that you have a deflection like this. So now you have, so that's case B, this is case A. And so in this case A, in case B, of course, you have a negative, a positive.
The deflection in this case B is because of what?
Because the horizontal, because the phi velocities are larger than the theta velocities.
Ah, the theta velocities are deflecting the
Yes. And so a good proxy for the, or that's what you get out of mean field theory. If you calculate mean field theory, what you actually find is that u theta u phi is equal to, and now I may get this wrong. You have 1, and then you have u theta squared minus u phi squared. And then this is squared.
No, it's 2 times all vectors.
So then, so that's simply with a plus sign or with a minus sign? So now we have, we just argued in the plus here.
Zach, so is your case being right?
Hmm?
Is your case being right? So right now, let's say it's a rotation in case A. We can have the same.
So here we have,
Sorry.
yeah, so here they are really different. They are rotated, but they are. But the question is which is the one of which is dominant, yes. Any other questions? Maybe one comment is about the Prandtl number. It is perhaps remarkable that Petri finds that ut over chi t is 4.5. What would you expect based on classical smoothing? You know, does anybody remember the answer? I'm not talking about what everybody else thought, but I'm talking about classical smoothing. So the theory, yes. So the theory is that chi t is exactly like eta t, and it is 1/3 times tau times u squared, that you may have seen, right? And if you do the same thing for this one, then it is tau times 2 divided by 15 times u squared. And the reason is for this difference is the fact that in the momentum equation, unlike the magnetic field equation, there's something weird, like which is called the pressure term. And the magnetic, and you don't have pressure terms in the other equations. And that really makes a difference. If you remove the pressure term, you have Berger turbulence. And the prediction would be that for Berger lengths you would be having 1/3, but nobody has ever checked that.
Is this the same in both cases here?
What?
Is this the same in both cases, anti-solar and solar rotation?
You mean this result? No. Each one case maybe.
Yeah, it's only one case of
So this is.
I mean, the anti-solar applies to be much more.
So this is the run number 4 or something like this here.
No, it's A0.
A0.
No rotation.
There's another result which was 1. That's the paper by Youssef and myself and Rüdiger in 2003. And because Youssef was in Norway and Norway no longer pays membership fee, he had to pay a hell of a lot of, his department had to pay a hell of a lot of money.
So it's expensive to reach these two.
He was even in the mechanics department. So this poor guy was in the mechanics department, and then they said, yeah, but why should mechanics pay for this stupid decision of the Norwegian astronomers? They shouldn't. I mean, our option would have been to simply withdraw the paper after the two papers we had actually. After both papers have been accepted, we should have withdrawn those.
Could you not select the maximum distance?
Yeah, but then it would have been refereed again, of course.
Yes. No,
But then you would need 1/3, right?
And then it would have
1/3
been,
of the shape there. Right?
yeah, then you need 1/3, yeah. Then it would have been 1 year later. Another question is, why does everybody do image this calculation with southern hemisphere? Right? That's just crazy. What's the answer?
Maybe because the digital stream.
What?
I think you did it also in the early 90s. So.
Yeah, so maybe you should ask me then.
Yeah, I think it's your fault.
So why did I do it? What do you think? I mean, the thing is, it actually has to do with what. I mean, it has to do with what I told you before, right? This one. So the, but not quite, because naively you would think maybe we are even in a. No, that's not right. This is even a right-handed system. So the thing was that we had a box, and observers always. I mean, as a theoretician, you think, of course, this is up, right? But the observer observes from here, of course. So he measures the depth instead. And we happen to put in, we just put a rotation. So somebody asks, what about rotation? And then of course we say, okay, we have this, and we put rotation upwards. And then we meet it in the size. That's it. So now, Patrick has another question.
Can I have the key?
What?
Can I have the key?
What?
Can I have the key to your door?
Oh, the door.
Can you just get me a key? So I don't have
Now
to
Patrick has a key.
But can Anna give me one or something?
I don't know, we have
A key for his door.
Yes, this is too dangerous. Because now we have access to Anne's office, for example.
So, what the hell would I do?
You know, change some value.
Change what? No, Anne has a secret gravity modifying device, and then I will change gravity so I can jump higher.
Useful glasses.
It's like in the James Bond movie, somebody had a secret